Okay, let's go on with pipeline. In this section, we will study pipeline through a designing example. That is the BIN2BCD converter. The function is you are required to design an 11-bit signed binary to BCD code converter. And the output for BCD code is 17 bits. The 11 bits signed binary is in the 2's complement format. So you must be familiar with this. And we limited the range to -123 to 123. We discard this number. Okay. And what is the BCD code? The defining of BCD code is as follows. For the output 17 bits, the first bit is assigned B. So if it's positive number, this bit is 0 and 1 for negative. Then there will be 4 bits to represent the digit for ones, tens, hundred, and 1,000. For each digit, it uses 4 bits, and the value range is 0 to 9. For example, if you input the hex 11 bits hex 0 to 0, that is 32 in decimal, then the output will be 16 bits hexamer in this of this number. The sign B, this is sign bit, and this is the 4 bit for ones. This is the 4 bits for tens, and this is the 4 bit for 100, and this is the 4 bit for 1,000. And in this case, this bit will be in the value range of 0 to 1. So you can say the binary format is friendly for computer, while the BCD format is friendly for human. When you want to display some binary value on screen, you may use the BIN2BCD converter. Yeah, this format is very friendly for human to understand what a number it is. And for this example, 11-bit in hex format 79C, that is -100 in decimal, and the output is the sign bit and the decimal digits for each. Well, this is the function of the problem. And you are required to design a block with I/O signals like that: clock reset, bin input, and bin value. Then you have to output the BCD value and the BCD value. The signal define is this is the input, this is the output. The valid signal here is used to quantify which cycle there is a valid input and which cycle there is a valid output. Okay, so let's say some sample waveform. So this is the input, the waveform for input, and this is the waveform for output. You may have some latency. Yeah. This is the latency from input to output. So you can have a fixed latency for the input to output. If this cycle is k, then the cycle here to here must be also k cycles. Yes. And this is also true for this. Yeah, for this should be k cycles. And the valid signal will toggle. Yeah, it can valid or invalid at any cycle. So there may be consecutive valid, and there may be 1 wait cycles, 2 wait cycles, or 3 wait cycles. There is no restriction on the waveform of being valid. Okay, this is a problem. I think you should have understand the design requirement. So, how to design this function? Please think about it. Okay, please take your time to think about how to design this function. And I will go on. I have figured out some algorithms. The first algorithm is using lookup table, or something like a ROM. So the method is, we have the bin value, then I will do absolute calculation on the bin value. Then I will get the sign flag, and the absolute value. Then I will use the absolute value as address to this ROM and get the BCD value of these amps. So this is the algorithm of lookup table. This is the lookup table. This is algorithm 1. And for the 1000th digit, it can be value 1 or 0. So you can use a comparator to decide the value for 1000th digit. So you can omit the looking of 1000th digit from the ROM. Then if you omit this part, then the ROM size will be 1024 plus 12 bits. Yes, we just look for the 100 and tens and ones bit. So the output is 12 bits and the input will be in the range of this is the range for the absolute value. So we get the ROM size. Okay, when you have an idea, you have to analyze the PPA, power performance area, for this idea. For the LUT algorithm, the hardware architecture is simple. Yes, it's straightforward. But there is 2 problems for this algorithm. The first is the depth of the ROM will increase greatly when the bit number increase in the input bin. For example, now we just have 11 bit of input. If it increased to 16 or 32 bits, can you calculate the depth of the ROM? Can you calculate? Yeah, for this, it may be in the depth of, yes, for this. So this is something too huge. And the width of the ROM will increase when the bit number increase in input bin. Yes, this is of course. When the bit number of bin increase, then you will have more digit for the BCD code. For example, you need to have the tens of thousand digit and hundred of thousand digit. Yes. So when the bit number of bin increase, the area of this algorithm will increase greatly. That means this algorithm is not scalable. Okay, and let's look at the algorithm 2. In this algorithm, I want to use divider to implement this function. First, I also calculate the absolute value. Then I use a divider to get the remainder and the quotient. This is the divider by 10. This is the remainder and this is the quotient, and the remainder here should be the BCD code of ones. Then I will reuse this value, reuse the quotient. I will reuse the quotient from the first step and use it to divide by 10 and divide the quotient, the bin underline S1 by 10. Then get the remainder and the quotient again. So this should be the BCD code for tens. The first divider, the second divider, and the third divider. Then I will reuse the quotient of the second divider and divide it by 10. So this remainder will be the BCD code for 100. And for the remainder here, the bin underlies S3. This is no need law. For this problem, this value must be the range of 0 to 1. So this is already the BCD code for 1000. Okay, this is the algorithm using divider. So can you analyze the PPA for this algorithm? Yeah, the calculation flow is clear, but the area is big for divider and the delay is also big for divider. Yes, we have talked about the area and delay for divider in chapter 1 of this course. So this is a problem. Well, in this case, the divisor is a fixed number of 10. Yeah, it's a fixed number of 10. So this may give a little smaller and faster logic, but I'm not sure. You can try it by yourself. Okay, is there any other algorithm for this problem? Okay, I have figured out algorithm 3. I call this method enumeration algorithm. So let's say they say like pseudocode below. This is the first part. This part we will calculate the BCD code for 1000. First, we will also calculate the absolute value. Then, the absolute value will be compared with 1000 to get the BCD code of 1000, and I will calculate the remaining numbers. And this is the second part. This is the second part. Calculate the BCD code for 100. So you can say they just compare with each 100 numbers, such as 900, 800, 700, 600, 500, 400, 3, 2, 100. For each compare, if the condition is true, I will get the BCD code for 100 and calculate the remaining value by minus this number. So I just test the value with all the 100 values. So I call this enumeration. And for the BCD code of tens, so I will use this value, yes? Yes, I will use this value to test it with 90, 80, 70, 60, 50, 40, 30, 20, and 10. Yeah. And for ones, this will be simple, okay? This will be simple. Okay, let me show you the code here. Oh, sorry, there is no code. Okay, you have to figure it out by yourself. Okay, this is the enumeration algorithm. So, can you figure out the hardware architecture for this algorithm, or the hardware block diagram for this algorithm? Can you figure out? Think about it. Let's also analyze the PPA for enumeration algorithm. The calculation flow is a little complex, but it just contains subtractors and marks. Okay, you will first figure out the architecture, then you will get this conclusion. There is just, you can say they're just subtractors. And this if, else if, else if, else if, else if should be marks. Yes. Okay. So I think the area should be smaller than the LUT and the divide algorithm. And for each level, such as the level to calculate the BCD code for 100 and the level to calculate the BCD code for tens, their subtractors are parallel. Yes, for these subtractors, you can use 9. You can use 9 parallel subtractors to compare the bin apps value with 900, 800 down to 100. Yes, these subtractors are parallel. They are not cascaded with each other. So the delay should be smaller than the divide algorithm. Yes, in divider, the subtractor in divider is cascade, not parallel. Okay, this is the PPA analysis for enumeration algorithm. So, how about algorithm 4? Yeah, you have to find it out by yourself. Can you find, is there any other algorithm for this problem? Okay, try it. Then, after the study of the algorithm, we will go to the architecture defined for this problem. Before that, let's review the principle of pipeline. So this is a function. You can say this is a function of 4 to 1 max. So you can insert pipe registers into the logic, into the combination logic to maximize the frequency of the circuit. Yeah, this is the original circuit and this is the pipeline circuit. We have insert pipes registers here. But the function of the two circuits is the same a lot. Yeah, if you can get the answer quickly, I think you have mastered the fundamental of pipeline in last section. If not, you must miss something in last section. Okay, the circuit is not right. It should be something like that. That is, the bit 1 of select should also be pipeline. So that means all the inputs should have the same pipe latency to the output. Yes. For this case, the pipe latency is one cycle. So the bit 1 of select also need to have 1 cycle latency from input to output. But for this circuit, the bit 1 is 0 latency. Yes. 0 latency to this point. Okay, can you think out the pipeline architecture for the lookup table algorithm? How to pipeline it? Yes. This is the block diagram for the lookup table algorithm. So how to pipeline it? First, you can insert Yes, you can insert a register after that. So this is the bin input, then you can insert a register. So for this cycle, you calculate the absolute value and get the absolute value and sign value. You use and register here. Then next cycle, you use the amps value and address to read the ROM. Yes. So this cycle you will assert the read enable of ROM to high, and this cycle the D out will be output from ROM. So you can say inside the ROM micro there is a pipeline. There is one cycle pipeline, or you can say there is 1 cycle latency. Okay, then and this cycle you will get the value here. Okay, you will get the value here. Then you can choose to register the value again to output it. This is the value here. This is the value at this cycle. Yes. Okay. So this is the earliest stage. We used to calculate the BCD value for 1 input. And for next input, we can do the same thing. We can do the same calculation flow. Calculate the apps value, then read the ROM, then get the D out, then get the ROM D out, and register it again to get the output. So this is a calculation flow for the second input. This is for the third and the fourth. So you can say for pipeline, you will divide the operation. You will divide the whole operation to several segments. Yes. And insert register between each segment. And from the view of one cycle, yes, from the view of one cycle, you can say different inputs will be in different calculation stage. The newest one here is just latch the input, and this one is in the stage of apps value calculation. Then this one is in the memory, in the ROM read stage. Then this one is latch the D out stage. Yes, we just get the D out from ROM and we'll latch it, we'll register it. So from the view of one cycle, different inputs will be in different calculation stage, and for each calculation stage, there is just one input at this stage. So this is the character of pipeline. Each pipe stage will do calculation for different inputs. And you can say from the input to output, there will be some cycle latency. Yes. After the pipeline is filled with data, that is, after some cycles, about 3 or 4 cycles, there will be output cycle by cycle. Yes. So these are the characters of pipeline. Okay. If you have understand the pipeline for LUT algorithm, can you define the pipeline? Can you define the pipeline for divider algorithm? Can you draw this? Draw a picture, something like that. Okay, let's go on. This is the pipe stage designed by me for divider algorithm. Okay, this is the algorithm here. So typically, I just divide this 3 divider into three stages. So first, I calculate the apps value and assign them. This is the first divider. In the first divider, we will get the value of. In the first divider, we will get the value of bin_s1, and BCD underline S0. Yes, S1, S0, BCD value. This is the BCD value for the ones. Okay. This is the BCD code for ones of BIN0, Then for next stage, we'll use this. We will do the calculation of second divider and get the value of BCD 0 underline S1 and BIN0 underline S2. This is the BCD code for tens. And the sign flag we have get here will be pipelined for each stage. Then this is the third divider. Yes, third divider. Then finally, after the third divider, we will get all the BCD code for each digit. So this is the calculation stage for first bin. Then this is the calculation stage for second, third, fourth. So in this stage, the first divider, second divider, third divider, then get the final result. And also, from the view of a single cycle, you can see for different bins, it will in different stages of the calculation. Yes, this is in the first divider. This is in the stage of second divider. This is in the stage of the third divider. And this is in the final result stage. And after some cycle of latency, the output will be output cycle by cycle. That is, every cycle we will get one result. Okay. Can you define the pipe stage for enumeration algorithm? You can pause the video and draw a picture like that to define the pipe stage for enumeration algorithm. I will go on. Okay, the first stage is the same. We calculate the absolute value and add a register here. After the absolute value, then we will compare it with 1000 to get the BCD code for 1000 and get the remain value. Yes. Yes, get the BCD code for 1000 and get the remain value. So this marks will select both the BCD code for 1000 and the remain value, labeled as bin underline amps. Then in this stage, we will calculate for the BCD code for 100. Yes. So there will be 9 subtractor parallelly compare with each 100 values, such as 900, 800 down to 100. So this marks should be a 10 to 1 marks. It will select the BCD code for 100 and the remain number. So you can say there is totally 10 branches. Yes. So this should be a 10 to 1 mux, but the mux is not parallel. Yes, this should be a cascade mux. As then if else, there is priority for each branch. Yes, this one has the highest priority. This is a little lower. This is the least priority branch. Okay, then after that, you will also have 9 parallel data comparator to compare with 90, 80, 70, and down to 10. Yes. So the block diagram will be something like that. So this is the stage to calculate for BCD code of tens. Then you will get the final result. And the dashed line here, this dashed lines represent for the pipeline register. We put a register at this point, and this point. Okay. So there will be registers, pipeline registers. Yes. Okay, this is the whole view of the pipeline architecture for enumeration algorithm. This is a pipeline diagram. Input, then the first stage calculated the amps value, and this is compare for 1000, compare to get the 100. This is compare to get the ones digit. And keep in mind that you have piped these signals. Yes, pipe these signals to the last stage. Then after the calculation for ones, we will get the final value at this cycle. By the way, I want to give you some guidelines of how to pipeline a design. From the 3 pipeline examples, we can say, before we pipeline the design, that is before we draw the diagram here, the first thing we need to figure out is you should figure out the pure combination logic circuit for this problem, for this design. So that is before the pipeline of the design, we have the pure combination logic architecture, a circuit for this design. Yes, the lookup table, the divider algorithm, and the enumeration algorithm. We have the pure combination logic implementation of these algorithms. This is the first key point. You must have the pure combination logic digital circuit for this algorithm or for this function. Then you just insert registers and into the combination logic. Then you get the pipeline design. So this is the steps to design the pipeline of a design. First, think out the pure combination logic circuit. Then insert registers into the combination logic data path. Okay. Okay, we have analyzed the hardware architecture for 3 different algorithms, and I choose the pipeline enumeration architecture. I think this should be the smallest implementation within the 3 algorithm, and it should get higher clock frequency, and it's scalable. That is, when increase the bit of input and bin, it's easy to extend. There is not much overhead on area and delay. But the enumeration algorithm and architecture may not the best algorithm and architecture for this problem. There may be better algorithms. Okay. When you have understand the problem and analyze the algorithms for this problem and define the architecture, you have to implement it in real code. And after that, you need to design the simulation environment. So what's a good simulation environment? Let's review. A good simulation environment can generate enough test stimulus to cover all the test points of the DUT. Then, after the simulation is ended, you can say that you can make sure the DUT is bug-free, and it also needs to include a RISC model in it and a checker, so it can automatically check the output of DUT and tell the simulation is fail or pass. So a good simulation environment must have these things, must have these functions. So let's analyze the test point for this problem. I think first you have to cover all the bin values of the input. That is from -1000 to 23 to 1023. That is about totally 2047 numbers. So this number is not big, so you can cover all the values. Yes. And you should have random value for being valid, such as you may have 1 to 8 consecutive active cycles. Then you can also have 1 to 8 wait cycles between active cycles. That means that means you can have 1, 2, or 3 or more consecutive cycles for being valid, and you can have 1, 2 or more consecutive wait cycles for being valid. Yes, you have tested the combination of valid and invalid cycles for being valid input. Okay. Okay, of course, you can figure out more test point in this problem. Yeah, the test point you are interested. Okay, that's all for this section. After the course, can you find is there any other algorithm for this problem? And please implement the pipeline hardware for enumeration algorithm in Verilog. Yes, practice, code it. You have understand the algorithm, pipeline architecture, then implement it in Verilog. And after that, please design the test bench for you design, and try to generate enough stimulus to cover all the test point and add a RISC model in your environment to automatically check the result of DUT is right or wrong. Okay, that's all for this section. Thank you. There is some homeworks.